Okay, so welcome to this next video in the Theory of Probability playlist. In this video what we're going to do is continue on talking about order statistics, and specifically what we're going to do is try and work out the PDF of an order statistic, so an arbitrary order statistic. What you could do is, we found the CDF in the previous video, and what you could do is you could just differentiate the CDF to get the PDF. But instead of doing that, what we're going to do is do it from a more intuitive standpoint so that you get a better feel for order statistics. Okay, so firstly I'm just going to remind everyone what an order statistic is. I know we've done this 3 times now, but it's worth repeating again and again. Okay, the idea is that you have some abstract probability space here, which, for a good intuition for having that, for what this is to think of it as the entire human population. Although, as we've discussed, the entire human population is actually a discrete probability space because, you know, it's got a finite number of people in it. But it's so big, you know, 7 billion, that you can approximate it rather well as a continuous probability space. But more abstractly, it will just be it might be a continuous probability space, i.e. it might not be the human population. And basically what you have is you have some random variable, which I will call h, which ascribes every outcome in this probability space, or every person that you could pick. So your experiment in this case would be picking a person from the human population, and the random variable big H is going to ascribe every person, every outcome that you could have picked, it's going to ascribe a real number. And basically this random variable big H is going to be distributed in some way. So let's say that it has PDF little f big H as a function of little x. So that just ascribes to every real number the probability density function of getting that real number, basically. Okay, so now what we then look at in order statistics is we look at a new probability space, which we'll put down here, which is the probability space of all possible samples that you could take, basically, of this probability space up here. So basically, we're going to say we take a sample of big N people. So we pick out big N. So to make it concrete, let's imagine big N is 10. So we pick out 10 people from the human population, and we record out what their values of H are. So we basically make a list. So, for instance, if H was standing for height, which is the intuitive one that we would imagine, then we might record it in meters. So we might get 1.8, 1.7, 1.5, 1.54 maybe, and obviously you'd record all the way up to big N of them. So this was the first person you sampled, so you picked him at random, and of course the probability that you get a certain real number is distributed like this, and you continue on basically until you've got big N sample points. Now more generally, of course, all you've got is this probability. More generally, you can have any old probability distribution here, and you are just sampling from it, and the probability, that density function, that you'll get a certain value is given by this here. Okay, so what we then talked about doing is we could set up random variables which we labelled x subscript I. So these aren't the order statistics. The order statistics have the brackets around them, and x subscript I is just going to map you onto the real numbers. It's going to take every sample in this probability space of all possible samples, and it's going to ascribe it the value of the ith sample point in that sample. So basically, xi will take a sample, which I'll denote by s, and it will ascribe it the value of the ith sample point. So basically, it will go along ith sample. Basically, if this is our sample, it will whatever I is. Let's say I was equal to 4, then I could equal anything from 1 to big N, basically, and it will go along and it will say, okay, this was our first sample point, this was our second sample point, this was our third sample point, this was our fourth sample point. So it will map this sample onto the value of that ith sample point, basically. Okay, so all of these random variables xi, no matter what I is going to be, are going to, firstly, they're all going to be independent. So x1 is independent of x2, so the value of the first sample point does not affect the value of the second sample point, etc. The value of the third sample point does not affect the value of the fourth sample point, so they're all completely independent, these random variables x1, x2, x3, all the way up to x big N, and they're all identically distributed, so they are independent and identically distributed, and they are distributed in exactly the same way as h, basically. So xi are independent and identically distributed, and they're distributed in the same way as the original probability space from which we're sampling. So basically what you're asking in each case is what's the probability density that I get a certain value for the ith sample, and that's just going to be this original probability density function that I got a certain value when I picked out a random sample. And the reason we like continuous probability spaces, or ones that are so big that they can be modelled as being continuous probability spaces, such as the human population, is because it means that these random variables x1, x2, x3, etc., they are truly independent. Because if you've got a discrete one, say you've got 20 people from which you're sampling, and you're taking a sample of 10, then basically the probability of the second sample point being a certain value basically is going to be affected. It is going to change potentially once you've taken the first sample, because if you've removed one person from the 20 that you were sampling, that's one person gone, and that will change the probability distribution that you'll get certain height values potentially, and therefore the distribution for this random variable x2 may well be different to the random variable x1, so basically they won't be independent in that case, and they won't be identically distributed. So that's why we like continuous probability spaces in the topic of order statistics, because they are all of these random variables x1, x2, x3, they're all going to be independent and identically distributed. So more generally, when you're doing order statistics, what people will say is that you have a certain number, 1 through big N, of these random variables xi, which are all independent and identically distributed, and they'll give you the probability distribution, and then what they'll ask you to do is find the order statistics. So the order statistics, which are denoted x parentheses in the subscript I, like so, what they do is, again, they map you onto the real line. So here's the real line, and basically they take any sample, so x parentheses I takes any sample, and it maps it onto the ith smallest sample point. Sample. So basically what it does is it takes sample point, I should put, rather than sample. So basically it goes to any sample in this probability space of all possible samples, and it says, okay, I will look through all of your values and I'll put them in order of put them in increasing order, basically. So at the moment what they're in is they're in the order that I picked them. So at the moment each sample is listed in, I picked this 1.8 as my first sample point, I picked 1.7 as my second sample point, etc. It's listed in the order in which you actually sampled them. What you can imagine doing is reordering those, because you've got a finite number of things, so you can certainly reorder them. And you can imagine reordering them so that they are now in increasing order. So in this case, you'd put 1.5 at the bottom, 1.54 then second, 1.7 third, and 1.8 last. So you can imagine reordering them so that they are actually in increasing order. And then basically the ith smallest one will be the ith one along from the left, and this random variable is going to map you onto that value. And we want to know, how is this random variable going to be distributed? I.e., what we would like to know is what is the probability density function of x subscript I, i.e. the ith order statistic. What is the probability density function of the ith order statistic? Okay, so that's our task for this video, to try and work out the probability density function of the ith order statistic. Now, if we recall what the probability density function is, it's a function on the real line. So here is the real line, and basically it's going to take every point, little x, in the real line, and it's going to ascribe it some value, which doesn't necessarily have to be between 0 and 1. But what does that value mean? It's not a probability mass function, so it's not as intuitive as in discrete probability spaces. Instead, what it is, it's a probability density function. And what that means is, basically, if you take a little point further on, if you take a little interval like this, so if you take this little interval here, which is of length delta x, so this is of length delta x, then basically if you want the probability that the ith order statistic is within that little interval, if you make delta x very, very small, then the probability density function evaluated at the point little x times this delta x, which should be very, very small, is approximately going to equal the probability that you are within that pink interval, basically. So this, by definition, this should equal the probability that the ith order statistic is within this absolutely tiny little interval, basically. Okay, so that's the way we're going to try and work out what the ith order what the PDF of the ith order statistic is. Okay, so now what we can say is, how do we work out the probability that the ith order statistic is within that pink little interval? Well, if we think about what we're doing, we are taking a sample. So let's think about taking our sample. We have our sample. I will just write it x1 of s, the first sample point that we took, the second sample point, because remember, all of these random variables, these xi's, are mapping each of the samples onto the value of the first, the second, the third, the fourth, etc. So we could just write our sample as x1 of s, x2 of s, x3 of s, etc. Okay, and basically, if the ith order statistic is going to be within this interval, then that means that the ith smallest one of these was in that interval. So firstly, you need to, if you want to know what is which of these samples is going to satisfy the condition that the ith order statistic is within there, well, that implies that one of these values, one of these sample points that you chose has to be in that pink interval. So one of them, at least one of them, has to be within the pink interval. So you've got a lot of choices of which one is going to be in the pink interval. You have big N choices because you've taken big N sample points. So any of them, any of the x1, x2, x3, all the way up to big N, could have been in this pink sample point. Because remember, this isn't, at the moment, this sample isn't ordered in increasing order. This sample is just ordered in the order that we actually took the samples. But one of them has to be within this interval, x to x plus delta x. But you have big N choices of which one can be within that interval. So, big N times, now what we want to know is what is the probability that one of them actually is within that interval x to x plus delta x. Well, that's going to be the probability density function of h evaluated at little x times delta x. The reason is that what we are asking is what is the probability that if I take a random point from my probability space, which I'm sampling up here, what's the probability that the value of this random variable h is within the interval x to x plus delta x? Well, by definition, that's just the PDF of this random variable big H evaluated at little x times delta x. Okay, so that's the probability that a single point is within that pink interval. But of course, we don't care which of the n points is within there, so we're going to multiply that by n, basically. Now, that's not the only condition on this. We want to, basically, what we're trying to do, let me just, to reiterate, what we're trying to do is we're saying, okay, there's a subpopulation of samples in this probability space of all samples, which satisfies the property that the ith order statistic is within this probability space here. What we want to the ith order statistic is within this interval x to x plus delta x. What we're trying to do is work out what the probability of that event here is. So we want to work out what is the probability of that event. So basically, what we firstly need to do is work out what we need to work out is we want to work out what the probability density function of that is, really. So what we firstly need to work out is what is the probability of an individual, or what is the probability density of an individual sample in here which satisfies that event, and then work out how many of them there are. That's where the big N comes from. The big N is there because you could have picked any of these n samples to have been the one that was in the ith order statistic. So this is the probability that was in this this pink interval. So this is the probability that one of them is within the pink interval. But there are n possibilities for which you could have chosen to be in that pink interval. So that's why we've times it by big N. Okay, what we then want to do is, that's not enough. Just having a single one of these in this interval does not guarantee that the ith order statistic is going to be within that interval. What we need is this one that we've chosen to be in the ith interval. We need it to be the ith smallest value. So that means that we need I minus 1 of the rest of these sample points to be to the left of the pink interval, which will mean that this is the ith smallest one. If I minus 1 of them are smaller, and then it's this one afterwards, then it will be the ith smallest one, and it will be in the pink interval. And then we need the other n minus I to be greater than this interval, i.e. to be to the right of this interval. So the n minus I need to be over there, and the I minus 1, other ones need to be over here, basically. Okay, so, but we don't know which of the I minus 1, one of them, we're going to pick to be on the left, basically. So what we could do is imagine now what we've done is we've picked which one is going to be within the pink interval. We now have to pick which of them is going to be to the left over here, which of them is going to be on this yellow side over here. What we've got is, imagine we've chosen 1 to be in our pink interval. So let's say we've chosen 1. So now the number that we have left is n minus 1 to choose from. So of all, big N minus 1 rather, oh dear. Big N minus 1 I over there as well. Okay, so we had big N original sample points, remember, and we've chosen 1 to be in the pink interval. We now have to choose from the n minus 1 remaining sample points which I minus 1 of them are going to be within on the left, basically, and then the rest of them are just going to automatically be on the right. Well, how many ways are there of choosing from n minus 1 things, I minus 1 things, where we don't care about order, I just care about which actual ones are to the left. I don't care about whether, as you're choosing I minus 1 of them, and I don't care if you choose which one you choose first, I just care about which ones you have chosen overall. So all you need to do is, for the first one that you're putting on the I minus, on this yellow side, there are how many possibilities? There are n minus 1 possibilities, because you could choose n minus 1 lots of these. Then for the second one, there's n minus 1, etc. Choices, because you've chosen 1 already to be on here, and now there's n minus 1 left. Of the rest of the remaining ones, that's how many you have to choose from to go to be the second one that goes on the yellow side. And then you continue on, and you need to choose. You need to go down so that you've got I minus 1 of these. So you'll have n minus 1 minus, and it will be I minus 1, basically, like that. In that way, what you'll end up with, basically, is I minus 1 overall terms, because here you've got 1 all the way up to I minus 1 terms, and then you add on this term, so you overall end up as having chosen I minus 1 things to go on this side. The problem with that is that this takes into account the different orders in which you chose them. I do not care whether you chose x1 to be on this yellow side in this choice here, and then you chose x2 to be on the yellow side in this one, or whether you chose x2 as your first one and x1 as your second one, and then identically onwards after that. Those should count as the same thing. This is counting them as separate. So what we then need to do is divide by the number of ways you could rearrange, the number of permutations of an identical choice of big N minus 1 things, basically. So you chose from big N minus 1 things I minus 1 of these sample points to go on the yellow side. And basically, if you write out a choice, let me give you an example. Say we chose x1s, x4s, and x5s. I do not want you to count that separately from x5s, x4s, x1s. That's imagining that I minus 1 is 3, so we've just chosen 3 things. So I do not want these to count as separate things. So what I then need to do is divide by the number of possible permutations, the number of ways you can rearrange a choice like this to just put them in different orders. And the number of ways you can do that is you can choose, imagine now, rather than it being 3, you've got I minus 1 things, so to generalize this. The number of ways you can do that is you can choose I minus 1 things to go in the first position. You can then choose I minus 1 things to go in the second position, etc., all the way down to the final one, which will be stuck where it is. So that gives you I minus 1 factorial, basically. It's the number of permutations, number of ways that you can rearrange all of these. And those I want to be counted as identical choices of the I minus 1 things which are on this yellow side. I don't want them to be counted separately. So I need to divide this by I minus 1 factorial, because basically at the moment I've counted all of those as separate. So basically by dividing through by this, I ensure that all of these separate things that were counted separately by this have all been condensed down into one, basically. Okay, and so this is actually equal to n minus 1 choose I minus 1. Okay, so that's just the definition of n minus 1 choose I minus 1. Okay, so that is the number of ways, basically, of choosing, so I'll put it in here. That's the number of ways of choosing from your n minus 1 remaining sample points. It's the number of ways of choosing I minus 1 of them to go on this yellow side. After that, the other n minus I of them are forced to go on the green side. And what we need to do is work out what was the actual probability that I minus 1 of them were on the yellow side. Well, what's the probability that that when you choose a sample point from our original probability space, what's the probability that it's on that yellow side? What's the probability that it's within this great big yellow interval here? Well, that is the probability. That's the probability that it is less than or equal to, what should I say, h is less than or equal to little x, basically, because that's this event here. This is the event that h is less than or equal to little x. So what we're asking is, what's the probability that when I choose an individual point, it's going to be less than or equal to little x? And that obviously is just the CDF of big H. Just by definition, that's what the CDF of big H is, evaluated at little x. And that will give you the probability that a single sample point is within this yellow interval. We want the probability that I minus 1 of them are within this yellow interval. Now, all of these random variables, remember, were independent. So basically, having chosen one that's in the yellow interval, it's independent of what your next choice is. It does not affect your next choice. So basically, the probability that I minus 1 of them are going to be within this yellow interval is just this probability that one of them is within the yellow interval raised to the power of I minus 1. Basically, just multiply this by itself, I minus 1 times, so that you've got it multiplied by itself, so that for each one of the I minus 1 sample points which are going to be on this yellow interval. Now, you then have to choose then what has to happen is the rest of them, the big N minus I, have to be in the green interval. So what we then need to do is evaluate the probability. We have to times this by the probability that big N minus I of them are within the green interval. Now, what's the probability that you're within the green interval? Well, that is the probability. If you make delta x really, really small, that converges on being the probability that h is greater than x, okay? If delta x is really, really small, if this interval gets smaller and smaller and smaller, that's what this probability of being in this green interval becomes, because this green interval basically becomes the event that big H is greater than x. And that is just 1 minus the probability that h is less than or equal to x, which is just the CDF of h evaluated at little x. So that is the probability that a single sample point is within the green interval. We want big M minus I of them to be within the green interval, so we need to have 1 minus the CDF of h evaluated at little x to the power of n minus I. And that, basically there, is the probability that the ith order statistic is within the pink interval. Because what we've done there is we firstly said, what's the probability density of a single outcome that has the ith order statistic equal to x? Within the interval x to x plus delta x. Well, firstly, what you have to do is this is the probability basically that a single point is within the interval x to x plus delta x, the probability density function evaluated at little x times delta x. So that gives you the probability that a single one of these sample points is within that pink interval. You then have to have I minus 1 of the other sample points within this yellow interval, and then the other n minus I. So that ensures basically that this is the ith biggest one, because I minus 1 of them are lower, and then this is going to be the ith biggest one. And then to make sure it is the ith biggest one, all the other n minus I have to be greater than it. it. What's the probability that I minus 1 of them are in this yellow interval? Well, that's this bit here. So that deals there with the yellow bit. And then what's the probability that the other n minus I are within the green interval? That's that bit there. And then all we need to do is take account of the fact that there are loads of possible different ways of achieving this same thing, which is you could have chosen big N different choices for the sample point that was going to be within the pink interval, so that's where that comes from. And you could have chosen n minus 1 choose I minus 1 for your choice of you've now got n minus 1 of these remaining sample points, which of them are going to be in the yellow interval and which of them are going to be in the green interval. So that takes account of the different ways in which you could choose these sample points so that they were in the yellow interval or the green interval. And basically, that is going to give you, this great big thing that I've got here is basically going to be the probability that the ith order statistic is within the interval x to x plus delta x, i.e. it's going to be equal to this probability density function of the ith order statistic times delta x. So now what we need to do is cancel this delta x on both sides, and we get that the let me move this up, that the probability density function of the ith order statistic evaluated at little x is going to equal big N, which is the size of the sample that you took, times the, in fact I'll put it in a nicer order, times n minus 1 choose I minus 1, times the probability density function of our random variable big H as a function of x, which remember is the probability density function that you will choose if you randomly draw out a sample, randomly draw a point out of our original probability space. It will be within, that's the probability density function that it will be at x, times the CDF of this random variable big H evaluated at little x to the power of I minus 1, times 1 minus the CDF of this random variable big H evaluated at little x to the power of n minus I. And that's a pretty cool looking formula because you've got the PDF in here and the CDF twice. So basically that is the formula for the probability density function of the ith order statistic.